problems. The first problem, which is from Easy Bucket, is symmetric tree. Has anyone tried or has any approach for this one? Or do anyone want to explain what the problem is? Hey guys, am I audible?
Yes,
Yes,
you are.
yes, you are audible.
Okay, I thought I was speaking to myself. Yeah, so let me share my screen. Okay. So here's the first problem for today, symmetric tree. So we are given a tree as an input, and what we have to do is find out whether that tree is symmetric or not. And by symmetric, what they mean is if you consider this 1, 2, and 3, 4, 3, 3 servers. So if you draw a vertical line at the root, you will find the mirror images of all elements on both the sides, right? So if you have a element over here at 1 in between, you'll find the 2 on each side. And if you have a mirror in this line, you'll have 4, 3, 4, and 4, 3. Okay. Now, if you go to the other one, and if you try to build a vertical wall here, at the first level, you'll see that 2, 2 is a mirror image. But if you see at the other level, it's not exactly mirror image. It's the same format. Like if you have, suppose you had a left child called as null, the mirror image would have been null 3 and 3 null, but it's not the mirror image. So this one is not a symmetric tree. Is the problem clear?
Yes. Yep.
Okay. Has anyone tried this? Any approach, any ideas, what to do, how to do?
Yeah, I've tried to solve this problem, but recursively I was thinking to compare the left and right subtrees. So let's say we start for the first tree, let's say we start at 1, and recursively we'll check whether the two childs, left child and right child, are equal or not. But this fails in case like on the third level. So because for again for first 2, which is on left, 3 can't be equal to 4. 3 has to be equal to the rightmost 3.
Okay.
The right child of the like 2. So that is what we want to compare. So recursively to compare that, I don't know how to check the value from the sibling and how to proceed.
Okay. Anything which you think, is there any way which you think you will be able to compare the first and the last element and the remaining ones? Any idea that comes into your mind?
Actually, we want to compare values on the same level actually. So that we can do by level order traversal. Again, if we do level order traversal of this tree, so on the second level 2 is equals to 2, and again on third level if we do level order traversal, so we get exactly like the string which we get or the numbers which we get are exactly the palindrome 3443, that is the property, and if it is there then it will be a symmetric tree.
Correct. So that's one of the approaches, like you can do a level order traversal, and at each level you can find whether it's a palindrome or not.
Yeah.
But that will fail for your second case if because that was also a palindrome.
Yeah, I'm coming to that. What will happen in this case?
Yeah, that will fail actually. Yep. We are interested in the position as well, not only in palindromic string.
Correct. Does this input format give you any idea about if we can use the palindrome feature?
This is a pre-ordered input, na? 1, 2, 2.
Yeah, I'm not saying the exact value, but I'm just saying the format in which this input is given. Can we use some idea from this input and try to have that pre-order approach or the level order approach implemented here also.
Puneet is asking you to look at the null and think about it, I guess.
Correct.
Or maybe we can substitute something like add a zero instead of a null in the string and then check whether it.
Your voice is not audible at all. Could you just speak a bit loud?
I'm saying that maybe like in the list of like the string that we're generating to check the parameter, we just need to check like on the level the left half is equal it's the mirror image of the right half or not. So that we can do by substituting instead of a null maybe something like a value or a placeholder kind of a thing in the string and then check on the level. Because on every level we know the number of nodes, so we can check this half equal to that.
Right. So instead of having null not represented in your level order traversal, you may substitute null with any character which is not in the tree. Let's suppose a dollar. In that case, your level order traversal will be $3 and $3. So can you now try and see whether you can create a palindrome?
Actually, this input thing is interesting because each level has 2 raised to power n elements. So like 1, then 2 elements are at second level. Then third level will contain 2 raised to power 2, like 4 elements. And it is starting from null 3, null 3. So this is not a palindrome on one level. So from here we can see that this won't be a symmetric tree. Am I closer?
Right, that's correct. So this is just a representation of tree. The input that is given to you is not a tree. It's actually a root of tree, right? So this is one of the ways Leetcode usually provides input in for the trees. If you see, this is a structure which is generally used by Leetcode for an input of tree. If you try to visualize it, you'll see the first node is always the root, and then you have corresponding children with them, the next 2 elements. And if they are one of them is null, it will explicitly light it as null, so that it's a one-to-one serialized, so they can directly serialize and deserialize it from that string. So I was just trying, if you can take the idea directly from that.
Okay.
So if we could replace the nulls here with something like dollar and then do a level order traversal, the initial approach that was discussed was take each level, try to find the entire string and see if it's a palindrome.
Yep.
Right? Then that makes sense. Yeah, that approach is fine. What will be the time and space complexity for that?
For level order traversal, it will take linear time to visit all the elements and linear space as well to maintain a queue.
That's correct. So any other approach?
Just a minute. Actually, in previous case, we were also checking whether it is a palindrome or not. Now, suppose your one level has n elements. You can only get O of n, like palindrome check is, you have to spend O of n time just to check whether it is a palindrome or not. If you do it for each level, so you are doing it out for so many times, it may become O of n squared.
It will be n log n, right?
N log n, yeah.
The height of the tree will be log n.
Yeah, height of the tree is 1 log n. So let me think. So 1 plus 2 plus 4. So you have this geometric progression, right? So because first level is just 1 element, second is 2. If you continue doing that, you have 2 to the power n minus 1. Like, yeah, so those many. Yeah, you can say that. Yep.
Right. So it will be n log n time complexity. That's correct. So any other approach where, probably we could reduce the time complexity, or any other approach where we don't have to compare at level and do something else?
I my thinking, I think I will have 2 pointer, one one move to the left and one move to the right at the same time. So kind of like one would traverse pre-order on the left side, and the other one would traverse what they call reverse pre-order. So I can compare them. So for example, I go from the first one, I go the 2 pointer point to 1, right? And then the next time, the left pointer point to 2, and the right pointer point to 2 on the other side.
Okay, so you're saying reverse in order, right?
Yeah. No, reverse pre-order. I mean, one going to pre-order,
Correct.
and the other one going to reverse pre-order. And, at each move, I compare the value.
Right. Let me check if there's if it will create any other cases. Like, let's suppose we have root as 1, we have 2 at the left, and okay, so you're saying pre-order. Let me share my screen. So let's suppose we have this 1. Here also. Then we have 3, 4, and 3. So let's try to see if we can create another pre-order traversal, which will give us the same output, right?
Okay.
Let's see if there's 2. Let's keep the right one as is. So here pre-order traversal will be 1, 2, 3, and 4. That's correct.
1, 2, yes.
So is this a valid pre-order again?
No, but when I traverse, I also have to compare the node too. So, so let's say for the second example, the left child of 2 is no, but the right, the right child of 2 on the other side is 3. So it's not the same.
Okay, so you're trying to compare from the left child, every left node will be equivalent to right node.
Right.
On the other end. Right, so we can do that. If we have this 3 and then there's 4. So what we are doing essentially is trying to compare for each child, left child of this one will be equivalent, it should be equivalent to right child, and the right child should be equivalent to the left child.
Right.
Let's go a level further. We have 5, 6, 7, and 8. And then we have 8, 7, 6, and 5, right? Now suppose we have done with this level, we know it's same. And we are now here. We are trying to compare whether it's, it creates a symmetric tree or not, right? So what will happen now? What will we compare? The last 2 ends or the first 2, or what will we compare?
The 3 on the left side and 3 on the right side.
Right.
Right. And now the next one will compare the 5 on the last level, left side, and the 5 on the right side.
Right. So essentially what we are doing is at every node, we are comparing its corresponding entry on the right and its left node on the left with right node on the right, correct?
Right.
So, okay. So if we try to create a, recursive relation or recursive property using this, could we do that?
Yeah, this is kind of recursive, right? Because I do on the left side, it will be pre-order. But let's think about, if we traverse the tree on the left side, the pre-order, what are gonna be? It'd be 1, 2, 3, right? And then when on the right side, we do reverse pre-order, and then we kind of can compare them. But
Right.
in this
So-
case, I do recursively.
Correct. So if you see the pre-order, it follows a pattern of you first visit the root, then you visit the left child, and then you visit the right child.
Right.
Right. And if we do a reverse pre-order, it'll take the
Root,
root, right child,
right, and the left.
and then left child.
Yeah.
Right.
Right.
And if you compare it with how you are comparing right now, isn't it similar? You're first comparing root, and then comparing the left child with the right child of the other side.
Right. Yeah.
Right. So if we find a pattern, or if we find a way to traverse both the trees at the same time, one in pre-order and one in post-order, and compare each of those, we are done with the problems, right? So let's say here we start with node 1, right? It's a single node, and then we can take the two childs that we have. Are they equal? There's only one, yes, they are equal. So we are done with that. Okay, and till this level, it's similar. Right? We are done with, if we are going on the left child, it's going to follow the pre-order, and this one will be reverse pre-order. Right?
Yeah.
Now what we have to do is take left child of this one. Let's take it's 3. And for the other iteration, we have to take right child. Are those two same? Yes. Let's move ahead. From right child, we'll see 4. From here, we'll see 4. Right? Both of them are same, right? Now, what we'll do, instead of comparing these only at this level, we'll also insert them in some sort of a queue where we can take up the next elements to compare. Let's assume that queue is here. Right? And we know once this level is done, we'll have to compare this element with this element, right? The children of these elements with children of these elements, this element, right? That's what you're, checking on the left child symmetry and checking on the right child symmetry means.
Yeah.
Correct? So what we'll do is, while we're comparing the values, we'll also insert them into a queue. We now know we have to compare 3 from the left child, 3 from the right child in the next step. And similarly, once we are done with these two in this level, right? Next two will be 4 from the left child and 4 from the right child. Once we are done with each level, what we can do is take the top 2 from the queue and try to expand them. Right? And the same approach goes. Now we have 5 and 5, which will be compared first. If they are equal, we'll put 5 in here. 5 from left, 5 from right. Next step is 3 has other childs. Right child of 3 will be 6, 6 from left and 6 from right. So everything is equal till now. We are in the symmetry. Now suppose we hit a situation where we don't have the left child of this one and there's only right child. So now based on the condition, it should have symmetry. There should be, both of the children should be there, which are not there. We can stop here and return false. So this is not a symmetric. But at any stage when we are processing and at the end we see there's nothing left in the queue to process, that means we have processed all the nodes and all the nodes are symmetrical. Does that make sense?
Okay, yep. So here we are like not comparing the palindrome. So this complexity would exactly be O of n.
Right. So what we are doing here is, instead of creating a palindrome and checking, we are traversing it from the ends only, right? From the two extreme ends and then trying to come in between. So essentially, if you are traveling in this way in the pre-order and this way in the reverse pre-order. So if every element is same, that is essentially your palindrome. And you will not start your next level till the current level elements are done, right?
Okay.
That's how BFS works.
So just by changing the insertion into the queue, we have achieved that. Like pushing into the queue, the sequence of insertion we have changed so that this can be achieved, because we are
Exactly.
inserting
Exactly.
in a
So we are
normal
not inserting in this way. We are inserting from the two different ends.
two different ends. Okay, yep, understood.